Welcome to SAL 3. Our next talk is called Reverse Engineering DisplayLink Devices. It's about Linux support for USB graphic adapters, and it's going to be held by Florian Echtler. I'm very excited to hear about that, so please give a round of applause to the speaker.
Okay, yeah. Good evening, everybody. Thanks for coming to my talk. My name is Florian Echtler, and I'd like to tell you a bit about what Chris Hodges and I have done in order to be able to use DisplayLink graphics cards on Linux and other open operating systems. So at first, I'd like to introduce you to DisplayLink devices if you haven't seen them already. They're actually quite useful. They're USB graphic cards, quite cheap, around maybe 50 euros. They have DVI output or HDMI if you want. And in contrast to other USB graphic cards which you could buy earlier, they actually do use compression in order to get more bandwidth out of the USB bus. And they don't offer any sort of open source drivers or Linux drivers. If you ask, of course, you get something like, yeah, we're working on it, but then you don't hear anything else. So we decided to just look how these things work and installed the Windows driver in a virtual machine on Windows XP and attached the device and listened with USB mon on the host computer. Unfortunately, as you might see from this excerpt somewhere from the dump, it's pretty much encrypted, so this is supposed to be just a black screen. And yeah, it's safe to conclude that this is some kind of encryption. Of course, this begs the question why they do use encryption at all, but this is for a different part, probably. Okay, so we were a bit surprised to see this and then thought about what to do next. So, of course, we cracked the device open and had a look inside and found exactly 3 chips. One really, really big ASIC, which you can probably see here if you look hard enough, which is this one, and besides just a DVI encoder and DDR RAM. So we didn't have the equipment to sniff any of the data going over the bus here, and we didn't have any tech to look inside the ASIC itself. So tough luck. We had to use some different method. Okay, so we had to try to crack the encryption in some way, and I'll try to tell you a bit about how we did this. The first idea is pretty simple. We just took the log, wrote a Python script to dump this to the device again, and we did this with the first initialization sequence, and what we got was a static Windows desktop image. So this already allowed us some conclusions. As the log worked on different devices, it looked that the encryption wasn't hardware dependent in any way. So crack one device and you've cracked all of them, which is, of course, a bonus. When you look at the data, which is sent to the device, then you have some small blocks around maybe at most 4 kilobytes, and we have 2 very big blocks. And these blocks have to be sent in the correct sequence, otherwise the device starts flashing wildly and crashes. And this, again, allows the conclusion that maybe a stream cipher is used here. So we just have a key which has a certain length, and data is always XORed with that key. And if you reach the end of it, then you just take the length modulus, the length of the key, and start again. We inserted some delays between the blocks, and therefore we saw that the first one of the 2 big blocks just clears the frame buffer, and the second block transfers the desktop contents. So this was pretty much where we were at that point. One interesting part was that all of this were in fact, USB bulk transfers. So everything the device does is bulk transfer, with one small exception, which is at the very start. When you initialize the device, then some control transfers happen which are not encrypted. So for example, what you get here is the readout of the monitor description. Here, 64 bytes are read twice and 3 bytes additionally, so you get a total of 131 bytes. This is the EDID block plus 3 length bytes, and this is exactly the EDID data of the attached monitor. So at this point, encryption doesn't yet happen. And there's one interesting control transfer in this entire initialization sequence, which is just 16 bytes of seemingly garbage. What's most interesting is these repeat after each device initialization, but sometimes after you restart the virtual machine, the same bytes occur again. So again, we started thinking that this might be a crypto key, and so here were some sample sequences which look pretty random. Now Chris had a really good idea, and we just entered those into Google. Why not? And and as you might already think, we actually got hits, and this was quite surprising at first, but after some reading, we found out that this is simply standard output from the standard Microsoft random number generator. So, of course, this also explains why you sometimes see it again after you restart the VM, because the system is exactly in the same state as during the last boot. For some additional information on this, you can read the link afterwards. But okay, so we were pretty certain at that point that this data is actually the crypto key. But of course, this didn't help very much at that point, because we still didn't know what the algorithm used for the encryption actually was. So we tried some very basic cryptanalysis, which is just to compare the crypto text with itself, shifted by a certain length. So you take some buffer of crypto data, and for half of the length of this buffer, you just compare byte in location 1 to byte in location 1 plus some certain offset. And if these bytes are equal, then you increase a counter. And the results were quite convincing. So you can see them here. So these are actually sorted by count. So it's pretty certain to say that the key length is 4095, because this is the maximum and all of the multiples of this. And this is, of course, 2 to the 12th power minus 1, as most of you might already have seen. And this points again to a specific kind of pseudo-random number generator, which is called linear feedback shift register. And this is also interesting because these registers are often used in FPGA and ASIC programming, because they are very fast, and so this might have been a convenient choice for the developers of this device. Of course, this doesn't help too much if you know the key length. Now, what you need in the end is the key stream generator. So our two assumptions were that we have a stream cipher, we have LFSR, random number generator, a maximal LFSR, which means that it actually uses the maximum possible period, so which is 4095 bytes. Okay, so now we had to try and find the keystream generator in some way, and we started with IDA Pro freeware to just disassemble the driver module. And we quickly found that it uses libUSB internally, which was statically linked into the driver, which might raise some interesting licensing questions. And yeah, the data was just submitted through one of the libUSB calls, and what we tried at first was to work backwards from there, look at the call graph, and look where the data actually comes from. Unfortunately, the driver was written in C++, and it's not that funny to try to disassemble virtual functions. in the end, we settled on a much simpler approach here, and we just looked for, in the assembler code, for an immediate value of 4095, because at some point the routine has to generate that much data. And we